Hello, this session continues our introduction to fundamentals of physical geography. As you can see on the screen here, there's a lot to come, lots of detailed information about lots of different topics. If you aren't already familiar with this list, have a look at the handbook because all the information you need about what's coming up is in there. Now, all those topics aren't just a random selection of bits and pieces, they're organised around a set of themes or big ideas, and we've broken the whole module down into sections, one section per big theme. So after this introduction where we're putting physical geography into context, we're going to talk about energy and materials and the fact that a lot of what happens on the Earth's surface is to do with this interaction between energy and materials. Those interactions drive and are involved in lots of global and local scale systems and cycles, and the processes that are part of those big systems and those broad scale cycles are what lead to the local conditions that we see around us, for example, in the form of our local landscapes. All of that is operating within the current environment, but the current environment changes over time, and the nature of environmental change and the way that environmental change is affecting the systems, the cycles, the processes and the landscapes is right at the heart of modern day physical geography. So that's where we're heading with a lot of our ideas in this course, is to give you a good sound introduction to how environmental change is impacting the physical environment and physical geography. And then we'll finish the module with some specific case studies that try to draw together these big themes and apply them to particular instances or examples. As you've already seen in previous sections of this module, our approach throughout is a scientific approach, and we're particularly focusing on the idea of systems as being at the heart of the way physical geography works. Now we've already talked earlier in this step about the content of physical geography and the approach of physical geography. I also want to just say a few words at this stage about the organisation of physical geography as a discipline. You're already probably familiar with the academic structures within which physical geography works. You're registered for bachelor's degrees, Bachelor of Arts, Bachelor of Sciences, and some of you might already be thinking ahead to carrying that academic career further into a master's degree, possibly even a PhD. And then, of course, there are careers in academia where you can continue this academic interest in physical geography. It's also important to recognise, though, that there's a professional structure to the discipline. For example, the Royal Geographical Society with the Institute of British Geographers organises the Chartered Geography scheme, which enables geographers to get professional recognition or a professional qualification that pays attention to their particular geographical skills. You could become members or fellows of the Royal Geographical Society, and you could then be entering into this big professional structure for the discipline that you are now a part of. From our point of view now as academics moving forward into the discipline, it's really important to recognise that geography is a research-based discipline. It isn't that everything is already known and we're simply looking it up and finding out what people already found out before us. We're actually entering into territory here where there are lots of unknowns, lots of things that we still need to find out. And as you're studying physical geography, you're not just picking up existing knowledge, you're entering into this exploration, this discovery of new things. And a lot of the reading that you do will be reading ongoing work, current work, active work in a very much live discipline based on research. Because of that, your reading won't all be based on textbooks. To some extent, at first year, textbooks will be really important in giving you the basic information, but increasingly as you work your way through your degree, you're going to be using academic journals and looking at the research papers that are published in those. And there's almost a hierarchy that you can think of, from the original research being published in academic papers in the research journals, through what we call review papers, which is where an academic draws together lots of published research and summarizes it in a way that provides you with a kind of state of the art or a state of the discipline report, and those are going to be very useful to you as students. And then at at the most basic level, if you like, are the textbooks that you can use to a large extent, find out those bits of information that we are already fairly confident about. And it's because textbooks tend to focus on that information where we're confident that they're not so much at the cutting edge as the research papers are that you'll be working with later on in your degree program. As part of this academic and professional organisation of physical geography, it's also important for you to recognise at this stage that there are conventions, and within the professional and academic world, systems such as peer review, where academics check each other's work, researchers check each other's work before it gets published. That's a really important part of policing the discipline, if you like. And we've introduced that for you at this level through things such as our house style, which require you to adhere to a certain set of conventions or standards within your writing. So it's appropriate at this stage for you to think of yourselves as entering into this existing structure, this academic framework and this professional framework, which can lead through to careers in physical geography. So a worthwhile thing to be thinking about at this stage is, where is it that you're used to getting your information from? As you move forward into university and you're studying in a different way and you're learning new things, how does what you're going to be doing in the future compare with the way you've done things in the past? So are you used to using internet sources or textbooks, or have you ever used academic journals before? Just reflect for a minute on the kinds of sources that you're used to using. And an important point that I would emphasize at this stage, and I'll give you some illustrations to explain why this is important, is that you start being really careful, if you haven't been already, to be aware of inaccurate or incomplete information. Be very careful with the sources that you're using and check the information that you're finding out. I'd just like to give you a couple of illustrations to show what I'm talking about there and why it's so important to check everything. This is an extract from one of the most widely used A-level textbooks where they're talking about the origin of a landform called a drumlin that you might have heard of before. It's a hill which is related to glacial environments. So there are lots of drumlins in the UK, for example, and we'll talk about those in just a few minutes. But let's look at this definition in the textbook about what a drumlin is and how a drumlin is formed. And they say the most widely accepted view of drumlins is that they were formed when the ice became overloaded with material. That's not actually true. That isn't the most widely accepted view of how drumlins are formed. But they say the most widely accepted view is they're formed when the ice became overloaded with material so that the competence of the glacier was reduced. Now, competence is an interesting term. It's a term that relates to the ability of, for example, a river to carry different sizes of sediment. So slow flowing water might carry clay and silt, faster flowing water, more turbulent water might carry sand or even gravel, and you'd need a really big flood to start carrying boulders. And that applies to fluid flow such as rivers. But it doesn't really apply to glaciers. If you imagine a glacier gradually trundling down its valley with a great big boulder sat on top of it, if the glacier slows down or stops, it doesn't drop the boulder is still sat on top of the glacier. Glaciers don't behave like rivers, and it isn't really appropriate to talk about the competence of a glacier. And it says, carrying on, the reduced competence may have been due to changes in velocity. Well, no, the competence, even if you did apply the term competence to a glacier or thought about the sediment transport capability of a glacier, velocity changes aren't really going to have an immediate impact on that in such a way that they would lead to the deposition of material. So it would be very easy to get a wrong understanding of how drumlins are created if you based your understanding simply on that description from one of the textbooks. We'll come back and look at drumlins in more detail in just a second, so you'll get an idea of how they are formed, or the discussions around how they're formed. But let's just look at another example first of all of where you might get inaccurate information if you don't choose your sources very carefully. And this is an example that does relate to fluvial situation, fluvial systems or rivers. And this is from a random study website, the kind of thing that I imagine you might have used in the past, but you need to be very careful of. And they say that deposition in rivers takes place when a river has insufficient energy to transport its load. So that's the same kind of story that we were hearing with glaciers, but in this case it's okay. That is how rivers, certainly how rivers work. If the river has less energy, it won't be able to transport as much material, so it might deposit that material. Deposition is greatest, it says, in the lower course of a river. Again, that's broadly speaking true. I have no problem with that. And deposition will occur when the speed of a river is reduced. Again, that's fine. This may happen in areas with a sudden increase in gradient. No, that's not right. That doesn't make sense, does it? If you suddenly increase the gradient over which the water is travelling, that's going to increase the velocity and therefore increase the sediment transport capacity of the river. So they've got it wrong. Maybe it's just a typo, maybe it's just a simple error, but what they mean there is that this may happen in areas with a sudden decrease in gradient. So it's just an illustration of the fact that you have to be really careful. So what would you do in that situation then when you've read something on the internet or in a textbook, or if your tutor has said something in a lecture? What do? You check it. And you check it, for example, by searching on Google Scholar or Web of Science. You've had separate classes, or you will be having separate classes on how to search for good, reliable academic sources. But for example, if you go onto Google Scholar and type in search terms such as fluvial, deposition, gradient, river, sedimentation, geomorphology. Make sure you're asking Google Scholar to give you just sources from peer-reviewed academic journals and see what it offers you. And here's an example. I just did that, and I just pulled up a more or less a random article that it offered me. And it's from the journal Geomorphology, which is a peer-reviewed journal, a journal where people have been checking the work before it gets published. And it's looking at fluvial processes and the morphology of the Brahmaputra River. And it explains there that the Brahmaputra River flows through the Himalayas, and the amount of sediment going into the river is very high, lots of sediment coming off the mountains into the water. But the slope of the river decreases when the river comes out of the Himalayas and reaches the flat plain further downstream. And there's a cross-section on the left-hand side here, basically showing a cross-section of the course of the river through the Himalayas, down out from the edge of the Himalayas and onto the flatter ground below. And here there's at this point, a sudden decrease in the gradient of the flow of the river. So you would predict, based on what we've just been talking about, if there's a decrease in gradient, the river at this point won't be able to carry so much sediment. Lots of sediment was put into it up here, so you would expect to have a lot of deposition in the river down there. So the next thing you might do is think, well, I don't actually know much about the Brahmaputra. I don't even know where it is. Let's go and have a look. Get onto Google Earth, get onto Google Maps, and just search for it. Have a look, have an explore, and you'll find the Brahmaputra comes through the Himalayas down onto the plain and flows out in this direction. But just go and have a look in the atlas. Go and find these places. Geography is about interrelations between places, distributions, locations. People say that geography isn't just about knowing where places are, but part of geography becomes a lot easier if you do know where places are and if you explore the characteristics of those places as you're learning about the processes and mechanisms and landforms. So go and have a look at this particular area. And straight away, even now, just as I'm looking at this, I'm thinking, well, the uplands, the gradients, the flat, the sediment coming out into the, oh, look at these deltas coming out into the, and straight away there's geomorphology jumping out at me from that image. So zoom it, find the Brahmaputra, zoom in and have a little explore. And on Google Earth or Google Maps or other packages, you can manipulate the landscape, zoom in, look at it in 3D, and just zoom in and have a look at what's going on. So here's the river coming through the mountains, down the slope, onto the flat ground, and as it comes onto the flat ground, you can see something's going on here. You're going from a single threaded channel where all the water is flowing together, carrying all its sediment, then down onto the lower land, the flat land, and the water is spreading out into different channels. You've got a broad braided channel pattern here, where each channel is a lot smaller than the big single channel up here. The gradient is lower, the energy is lower, material is going to be being deposited here. Let's look at that in 3 dimensions. So we just tilted the Google Earth view, and here again you can see the river coming through the mountains, down onto the flat ground below, and here spreading across the whole of the image more or less, and then another smaller one here from a different stream coming out from the mountains, you can see these fans of material, of alluvial material being transported and then deposited by the rivers in this fan shape at the edge of the mountains. These are alluvial fans, and they're exactly what you would expect based on what we've just been reading about, the decrease in energy available to the river to transport its sediment as it comes out of the mountains, carrying a lot of sediment from the mountains. So you've done your little bit of follow-up reading, learning about your particular issue of gradient and energy and sediment deposition. You found a case study. Keep going, explore the literature a bit more, find some more case studies. In this case, if you're looking at alluvial fans, well, in some of the standard textbooks, they talk about alluvial fans in some detail, and you'll see examples from all over the world. Here's one in Death Valley, and this is a road just skirting around the edge of the fan, but it's a similar situation to what we saw before. High energy stream full of sediment coming out of down a steep gradient, hitting the flatter ground, losing energy, spreading out and depositing its sediment. So you can find examples of that all over the planet. You can explore further and find examples of that on other planets. And here's a paper, again, just a more or less random paper that I dug out for you, just talking about alluvial fans on Mars in this case. There's a wide range of different locations, examples, sources, case studies for you to get out there and explore, and you can tie together the information from all these different examples to make sure that you have a clear, consistent, reliable understanding of the basics of those processes and those landforms. So don't just rely on one little definition from one side, which might be wrong and which isn't really going to make a lot of sense in your head if that's all you've got. Get lots of definitions, get lots of case studies, get lots of detail from different locations, and tie those details together into a nice package, if you like, of understanding of each topic. So a couple of key points to take away from what I've just been saying. First of all, the world is more exciting and more complicated, but that's a good thing. The world is more excited and more complicated than maybe you learned at school or college. Therefore, now that you're studying at university and you're really getting to grips with some of this complexity, you need to look at the world more carefully in order to see it more clearly and more correctly. That's really important now as you move forward. And as part of that, don't accept the first answer that you find or the first answer that you're given. Don't just believe what you read in the book. Don't just believe what your tutor says to you in some meeting. Go and check everything. Read more, explore, check stuff again until you're confident in your knowledge of these different topics. Now, I'd just like to take a couple of minutes to talk in more detail about one particular case study, this case study of drumlins that we mentioned before. So here's a little photograph of a drumlin, just showing you roughly what it is that we're talking about here. This streamlined hill, blunter at one end, gently sloping, more pointed if you like at the other end. Here's a plan view with contours, here's a cross-sectional view, and here's a photo of a typical one. And they seem to form underneath glaciers of certain types, and they're composed dominantly of glacial sediment. And there's been a lot of argument over many years about how drumlins are formed, and they're a really good example of arguments, if you like, what we call in what we refer to as a plural and contested discipline of geography, i.e. people have different ideas and they argue about those ideas, and that's how the discipline moves forward. So here again is a Google Earth image. This is just north of Kiel on the M6 in Cumbria, and you can pick out on this image, because I've kind of done the lighting from the side, you can pick out this topography. It's sometimes referred to as a basket of eggs topography because it looks like a whole series of little half eggs poking up through the landscape, and each one of these is a drumlin. Here's another example. This is from the northern coast of Western Ireland, and here the drumlin field is reaching down to sea level, reaching down to the coast, and so as it goes below the high water mark, you can see individual drumlins poking up as islands here in Clew Bay in the west of Ireland. So it's another classic type site, if you like, or a nice case study site of where we have drumlins in the UK. Now, there are lots of different, or there have been lots of different hypotheses or ideas for possibilities of how drumlins are created. And this is how science works, like we were talking about in the previous session. You have a hypothesis, you then try to test that hypothesis using evidence and logical reasoning to see whether it stands up or if it has to be rejected. And the three main hypotheses have been these. First of all, that drumlins dropped sediment somehow underneath the glaciers dropped sediment underneath themselves, and that sediment formed the drumlins. That was the original idea, if you like, that drumlins were simply glacial sediments. An alternative hypothesis that gained a lot of traction but also caused a lot of controversy was the idea that drumlins were actually not deposits laid down by glaciers, but were remnants of erosion underneath glaciers. So big floods underneath glaciers were supposed to have eroded out channels but left behind some areas that weren't eroded, and those were the drumlins. And there was a researcher called John Shaw, who is very well known for having forwarded that idea, and he and people who agreed with him were very much at odds with a lot of other scientists who had different opinions, and that was a big controversy for many years. A third hypothesis, and this is the one which is now becoming far and away the most widely accepted one, is that it isn't either deposition or erosion, it's deformation. Again, Google Scholar, drumlin origin controversy or something like that. You'll find lots of papers about these different hypotheses that you can just have a quick look at. Don't get bogged down, but if you just look at some of the abstracts, and I've given you one here that you could chase up, have a quick look at the abstract and it will give you a good illustration of how physical geography has been and remains plural and contested, in the sense that there are still things that we don't necessarily know. The drumlins debate is kind of settling down now, as you'll find when you do some reading on it, but for many years it really was an area of significant controversy. So this is John Shaw, the researcher who did a lot of work on subglacial floods, the subglacial floods hypothesis. And as you can see, he says that he thinks those floods may have been responsible for the formation of drumlins. But other people, so Dave Evans, who I'm very rudely covering up there in the bottom of the picture, people such as Dave Evans and other scientists disagreed with that and said that the mega flood interpretation conflicted with the evidence that he was proposing. And one of the outcomes of this dispute, this controversy, these arguments between different sides of the discipline talking about drumlins being formed in different ways, was this statement from Geoffrey Bolton, who's a very eminent glaciologist and geologist. And he refers to this debate between people such as Shaw and people who agreed with him, and people such as Evans and others who agreed with him. And he said that that dispute illustrated something which is really important in science. It exemplifies, he says, a problem that arises when speculation is unconstrained by evidence. Now that's a really important comment on what science is about and where things can remain unresolved. If we don't have evidence, we're not going to be able to sort out disputes between people who have different ideas. Having different ideas is great. Speculation is great. It's a way of coming up with ideas. But having speculated, having thought up good ideas, you then need evidence to test those ideas. So what does that mean for us? Well, what it means is that we need to consider evidence whenever we're thinking about alternative hypotheses, and we need to ask more questions. So on the drumlin one, for example, suppose you were trying to test John Shaw's hypothesis that drumlins were caused by massive floods that happened underneath glaciers. What might be something you might go and look for as evidence that could show that this was possible or impossible? If I say this was caused by a massive flood, what must there be evidence for in order for that to be true? Well, one thing you might have said there is, if they were caused by a massive flood, then we want some evidence of massive floods, and there needs to have been somewhere for the water to have come from, and there needs to have been enough water to do this job. So you might have asked the question, well, was there at some point in the past enough water underneath the glaciers that we're talking about for Shaw's idea to even be possible? And this is the kind of work that people have done. This is how science works. So Gary Clark here, working on the Laurentide ice sheet, which was the ice sheet that covered much of North America, Canada and the US, northern part of what's now the USA. This is the Laurentide ice sheet just towards the end of its time, as it's shrinking away to almost nothing. It was much bigger than this originally, but as it shrunk and retreated, melted, water ponded up against the edge of it, and this water occasionally flooded through underneath the ice to reach the sea. And Gary Clark did work looking at how much water would have been involved in these great floods. So that's an indication of the kind of work that one could do to get evidence to test and either support or refute hypotheses of different types. And that's how science works. And that's one of the fundamental characteristics of physical geography. We have ideas, we come up with tests, we use data or observations as evidence to test those hypotheses. Very briefly, I'm not going to talk about this in detail, but I'll put this slide up here so you can chase it up if you want to. But just to draw the debate a little bit towards a close, I'll just have this slide reminding you of what I said earlier, that deformation of subglacial sediment is now the most widely supported hypothesis. And if you do want to get into this, there's an awful lot of material that you can read, and you'll have opportunities to do more on this in subsequent years of your degree if you want. It's a topic that you can come back to, and it's a nice case study. So a key point at this stage is that the answers to whatever it is you might be trying to find out about in physical geography are not always simple and straightforward. And that's one of the issues, that's one of the things that makes physical geography really interesting. The answers at this level are not always simple and straightforward, and that's what makes things interesting. If we knew all the answers, it would be nowhere near as much fun. So as we approach the end of this slideshow, a couple of reinforcement questions for you. Work your way through these. I'll put them elsewhere so you can go through them in your own time. But just work through these questions and make sure that you've picked up some of the things that I was saying in the session, and make sure that you can answer these questions. Also, going back to the start of the last unit, the beginning of step 2, you'll remember I gave you a number of questions there to watch out for the answers to. So now would be a time to revisit those questions as well, and just make sure that you picked up the answers to those, or you picked up the discussion around those points as we move through this step. And finally, by way of conclusion, just a reminder of what you should be able to do right now based on what we've covered in the last few videos and the last few exercises that you've done. You should be able to define geography and physical geography and science. And for your definition of physical geography in particular, you should be able to define physical geography with reference to its subject matter and its method. It isn't just about the subject matter, it's about the subject matter and the method. You should also recognise how the subject matter of physical geography overlaps with other disciplines, and that's why you can't use the subject matter alone to define the discipline, because we share a lot of our subject matter with other subjects. You should now be able to describe the organisation of the discipline in terms of the institutions, the qualifications, the way that publications work. You should know a little bit about the professional as well as the academic context of the discipline. And if you follow up the reading that we recommended a little bit earlier on, you should also now be able to summarise some of the key figures in the discipline, identify some of the key figures in the discipline and in the history of the discipline, and to identify some of the key turning points at which the discipline changed over time. So there's lots to get to grips with at this point. I know we're giving you a lot of information to explore, but hopefully we're also giving you plenty of time to do that extra reading and to do that exploration around the subject before we move forward within the sessions to look at some topics in a lot more detail.